Okay, so the next section we're looking at is 2.4, which is the quotient rule. In the previous section, we looked at how to find the derivative when you have two functions being multiplied with each other. The difference now is, what do you do when you have two functions being divided, meaning we're using a rational function. In the previous video, I showed you guys how to convert any rational function into a product rule function, meaning you have two functions multiplied, but we should also know how to work with rational functions, meaning if there's a division. So in product rule, because you're going to add the two quantities, then it didn't matter which one you found the derivative first, whether you took the derivative of the first function or the second function. But in the quotient rule, because we're going to subtract, it's important to remember when we go over the formula, that you have to maintain the order. So the formula is simple. You have g at x over h at x, numerator over denominator. So you take the derivative of g at x, so the derivative of the numerator multiplied by the denominator as it is, minus the original numerator multiplied by the derivative of the denominator. And then whatever the denominator is, you square it. In this case, it's very, very important to remember that you're going to find the derivative of g at x first. The derivative of the numerator first, the derivative of the denominator second. Okay. Now, let's go ahead and apply this. This actually is going to be a very short video because applying the quotient rule, there is nothing really different about it. There's no extra rules to remember. It's very similar to the product rule, except that you have rational functions instead of polynomial functions. So let's take the first example. So let's take f at x, 2x minus 1 over 3x plus 2. To find the derivative, right, we find the derivative of the numerator, which is 2, multiplied by the denominator as it stands, so exactly as it is, minus, now the numerator stays as it is, and you multiply by the derivative of the denominator, which is 3, all over the entire denominator squared. Now, to find this derivative, to continue to simplify this, we're going to expand and simplify. So this is 6x plus 4 minus 6x plus 3 over 3x plus 2 squared. And for the most part, I would not expand the denominator, leave it as it is in its squared form, because sometimes you'll be able to cancel out, sometimes you will not. Now we have 6x minus 6x, 4 plus 3 is 7. So to find the answer would be 7 over 3x plus 2 squared. And that would be the simplified form of your derivative. Let's do one more example. Let's make it a bit more complex. So now we have 3x squared over 2x plus 1 all squared. Again, it is still a rational function, so the overall derivative, the overall picture is going to be quotient rule. I know when I find the derivative of this function, I'm going to have to use the power rule. And when I find the derivative of the denominator, I'm going to have to use the power of a function rule as well as the power rule. So let's find the derivative. We find the derivative of the numerator first. So bring the 2 down, multiplied by 3, that's 6, and then x to the power of 1, multiplied by 2x plus 1 squared, exactly as it is, minus 3x squared stays the same, and then multiplied by the derivative of the denominator. Review from 2.3, we bring the 2 down, this exponent comes down, so it's 2, and then 2x plus 1 stays the same, and then this becomes a 1, and then multiply by the derivative of what's inside the bracket, so that's just going to be 2. All of this over 2x plus 1 squared, and then we have to square whatever is in the denominator. Yes, it does look confusing, but this will simplify. Now we're going to expand and simplify whatever we can. Now here is a trick to remember. Instead of expanding 2x plus 1 squared and multiplying it by 6x, look to see if you can find the denominator in each part of the numerator. So I want to see if I can find 2x plus 1. Well, there's a 2x plus 1 squared here and a 2x plus 1 here. So instead of expanding all of it, what I'm going to do is, because in this case it's all being multiplied, and in this case everything's being multiplied, I'm going to take 2x plus 1 from here and factor it out. So 2x plus 1 comes out. When 2x plus 1 comes out, here I'm left with 6x, and then since one of them has come out, there's a 1 left. So 6x times 2x plus 1 minus, and then here we have 3x squared times 2 times 2. So 2 times 2 is 4, times 3 is 12. So I have 12x squared, because this 2x plus 1 is gone once you factor it out. So left with 2 times 2 is 4, times 3 is 12x squared. Close the bracket, all over 2x plus 1. And then 2 to the power, 2x plus 1 squared to the power of 2 is going to be 2x plus 1 to the power of 4. So this cancels out with this, and that becomes a 3. And now we can just simplify all of this to get 6x times 2x is 12x squared plus 6x minus 12x squared over 2x plus 1 cubed. So 12x squared cancels out. Final answer would be 6x over 2x plus 1 cubed. In the two examples that we've done, the leading coefficient have canceled out, the leading variables have canceled out, the ones with the highest exponent. That does not always happen, but if you're going through the process, this is why it's important to simplify. Do not leave it as it is in the beginning. Don't automatically expand. This is why I told you guys, when you're dealing with derivatives and you're simplifying equations, especially when you're dealing with the quotient rule, it is going to be important that you are comfortable with algebra and you are looking at all the different steps and trying to see how you can simplify. What's the most effective way to simplify, and not just regurgitating what we've been doing in the past, where it's just expand, simplify, expand, simplify. We do have to now look critically and see what is the best way to simplify. If we had just expanded all of this, it would have been very difficult to eliminate one of the 2x plus 1s from the denominator, and it would have resulted in a very long, complex equation in that you would be spending a lot of time trying to simplify. Whereas if we can see that the denominator exists in both terms of the numerator, we can cancel them out, and that simplifies our numerator. It's much easier to do it that way, and the denominator as well.